Chapter 7 Estimation and Inference. In many previous chapters, we stressed the point that it is not feasible, it is not possible to study the entire population. That's why from the population data, we take out a sample. We study the sample, and based on the sample, we derive some conclusions about the population. So in this chapter, we will be looking at various sampling methods. We look at central limit theorem and inference, and bootstrapping and the empirical sampling distribution. Section 2 Sampling Methods. Sampling refers to the procedure of drawing or creating samples from the population data to answer some questions about the population. So for example, if we want to find out on an average how much does each household spend on groceries. So suppose we are surveying United States of America. Suppose United States has approximately 1 million households. So practically it is not possible to survey each and every household to find out how much they spend on groceries. So suppose out of the 1 million household, we take sample. Suppose we collect data of 10,000 households, randomly selected from the entire 1 million household population. And from the sample data, we found out that on an average, each household spends about $5,000 on groceries. Then we can also conclude the same about the population, that each household in the entire population must be spending on an average about $5,000 on groceries. So we take sample from the entire population to derive some meaningful information about the population. Hence, we use sampling in order to save time and save money, because surveying the entire population is very time consuming as well as it requires lot of resources. Parameter refers to the quantity computed from the population data to describe the population. So this is the entire population, and if I calculate say the mean and the standard deviation, these are referred to as the parameters or the population parameters. And suppose out of this entire population I draw a sample, then the mean, the sample mean and the sample standard deviation is referred to as the sample statistics. So statistic refers to the quantity computed from a sample which describes the sample. So the data computed from the population is referred to as the parameter, and the data computed from the sample is referred to as sample statistic. We will be looking at two types of sampling methods, the probability sampling method as well as the non-probability sampling method. In a probability sampling method, every member, that is every observation of the population, have an equal chance of being selected. Hence, the sample generated from the probability sampling method is considered to be more accurate representation of the population. Whereas in a non-probability sampling method, every member, that is every observation, may not have equal chance of being selected in the sample. Hence, the sample which is generated from a non-probability sampling method may not be that accurate representation of the population. So in probability sampling method, we will look at 4 different kind of methods, and in non-probability sampling methods, we will look at 2 different methods. So starting with the probability sampling method. In this sampling method, we will be looking at simple random sampling, then we will be looking at systematic sampling method, then stratified random sampling and clustered sampling method. So starting with the simple random sampling, the sample selected under the simple random sampling is subset, that is, a portion of the larger population, which is created in a way that each element have equal chance of being selected. So suppose we have a population. Population size is represented by capital N. Suppose the size of the population is 1 million and we require a sample of size 10,000. The sample size is denoted by small n. So, to create a simple random sample, we randomly pick 10,000 observations from the population data. So, when we randomly pick 10,000 observations from the population to form a sample, then this method is referred to as simple random sampling and the sample is referred to as simple random sample. This method of sampling is particularly useful when the data in the population is broadly similar. The second type of sampling method is the systematic sampling, where we select every kth member of the population until we have the sample of the desired size. So suppose we have a population of 100 observation, capital N is 100, and we require a sample size of 20. So we take the population size divided by the sample size. In our case, it is 100 divided by 20, which gives us 5. So in a population, we select the every fifth observation. Suppose these are the observations. So we select the first observation. Then we select first, second, third, fourth and fifth. Then we select first, second, third, fourth and fifth. In this way, we select every fifth observation in the population to form a sample of the required size. In our case, the sample size required is 20. So the kth member here is the fifth member. So the sample created in such manner should be approximately random. That is, every member have approximately an equal chance of getting selected. So let us look at the third probability sampling method, which is the stratified random sampling. In stratified random sampling, the entire population is divided into subpopulations. These subpopulations are also called as stratas or cells. So the entire population is divided into stratas based on some criteria. So for example, if we have a population whose size is say 10,000. So based on some criteria, we divide the population into 3 different stratas. We have strata 1, strata 2 and strata 3. So suppose strata 1 has a size of 4,000. Strata 2 has a size of 1,000 and strata 3 has a size of 5,000. So we divide the entire population of 10,000 into 3 stratas based on some criteria. Now suppose we require a sample of size 100. Then what we do is, first we calculate the size of strata 1 relative to the population. That is, we take 4,000, which is the size of strata 1, divide it by entire population. So we can say strata 1 is 40% of the entire population. Similarly, strata 2 is 10% of the entire population and strata 3 is 50% of the entire population. Now in order to select a sample size of 100, we select sample in these respective proportions. So from strata 1, we select 40% of the sample size required. So we select 40 observations from strata 1, we select 10 observations from strata 2 and we select 50 observations from strata 3. So these observations which are drawn from the strata 1 or from each strata follows a simple random sampling technique. That is, each observation is drawn in a random manner such that each observation have equal chance of getting selected. When pooled all these samples together, we get our total sample size of 100. And this is referred to as stratified random sample. And the entire process is referred to as stratified random sampling. From each strata, a simple random sample is drawn in sizes proportional to the relative size of each strata in the population. Then the samples are then pooled to form the stratified random sample. The sample statistic of such sample, that is, sample statistic of a stratified random sample, have greater precision in forecasting the population parameter. Suppose we have a population of size 10,000 and it has a particular mean represented by mu, and we draw a sample of size 100. This is a stratified random sample and it has a particular mean represented by x bar. This sample stat does a great job in estimating the mean. We are actually interested in knowing the mean, but because we cannot survey the entire population, we use a sample, specifically the sample statistics, to infer about the population parameter. So when we have stratified random sample, the sample statistic of that stratified random sample does a great job in estimating the population parameters compared to other sampling methods. The stratified random sampling technique is very frequently applied in the bond indexing technique. Bond indexing refers to constructing a portfolio to replicate the performance of a particular bond index. For example, suppose we have a S&P 500 bond index. Just like we have stock indexes, we also have bond indexes. So suppose we have a S&P 500 bond index and this index has 5,000 bonds in it. A portfolio manager wants to replicate this bond index completely. That is, he wants to create a portfolio which is exactly the same as the bond index. So he wants to purchase 5,000 bonds so that the portfolio can replicate the performance of the bond index. If the bond index earns a 10% return, then the portfolio will also earn approximately 10%. But the problem with replicating a bond index completely is high transaction cost. Purchasing 5,000 bonds will lead to huge transaction cost. So fully replicating a bond index can be costly. So here SRS comes into picture. SRS can be used to construct a portfolio which can replicate the performance of the bond index without the need to purchase all the bonds in the index. So S&P 500 had 5,000 bonds in it. So using the stratified random sampling technique, suppose the portfolio manager created a portfolio with 200 bonds in it. This portfolio completely replicates the bond index. This portfolio has approximately the same characteristics as of the bond index. So suppose the interest rate sensitivity of this portfolio is the same as the bond index portfolio. The duration, the convexity, the characteristics exactly match or approximately match the bond index. So SRS can be used to replicate the bond index without purchasing all the bonds in the index. So let us look at the following example which relates to bond indexes and stratified sampling. Suppose you are the manager of a portfolio of bonds which is indexed to the Bloomberg Barclays US Government or Credit Index, meaning that the portfolio returns should be similar to that of the index. So you are exploring several approaches to indexing, including a stratified sampling approach. So you first distinguish among the agency bond, the US Treasury bond and the investment grade bonds. And for each of the three groups, you define 10 maturity intervals, 1 to 2 years, 4 to 6 years, and the last maturity interval is 20 to 30 years. So for each of the three groups, you have 10 different stratas. And also, you separate the bonds with coupon of 6% or less from the bonds with coupon of more than 6%. So This is the entire population. This is the entire population of the index. And within each index, we have 3 strata. The first is the agency bond. Then the second one is the treasury bond. And the third one is the investment grade corporate bond. And within each of the strata, we have 10 different strata representing a particular maturity intervals. So we have 10 different stratas under each strata. And within each of the strata, we have 2 more stratas, where one strata represents the bond with coupon of 6% or less, and other strata represents bond with a coupon of more than 6%. So the first question is, how many cells or strata does this sampling pan entail? So we have 3 stratas. Within each strata, we have 10 different stratas, and within 10 stratas, we have 2 different stratas. So we have 3 into 10 into 2. So in total, we have 60 stratas or 60 cells. Second question, if you use this sampling plan, what is the minimum number of issues? That is the minimum number of bonds the indexed portfolio can have. So we have 60 different stratas, and at least one bond should be present in each strata. So we can say that portfolio can have a minimum of 60 bonds in it. The fourth and the last probability sampling method, which is the cluster sampling. This sampling method is similar to the stratified random sampling in some aspect. Just like stratified random sampling, this method divides the entire population into some subpopulation, which is also referred to as clusters. But unlike stratified random sampling, which divided the population based on some criteria, here the population is not divided based on certain criteria. Rather, each cluster is a mini representation of the entire population. So in a stratified random sampling, we had various stratas, where each strata represent a certain part of population with a specific characteristic. Similarly, the second strata represented certain portion of the population which had similar characteristics. But in cluster sampling, out of the entire population, we have various clusters, and each cluster is a mini representation of the entire population. After dividing the entire population into various clusters, we arrive at the clustered sample using either the one-stage cluster sampling method or the two-stage cluster sampling method. For example, suppose we have a population whose size is 100,000 and we want to have a sample with a size of 2000. The sample has a size of 2000. So we divide the entire population into various clusters. So for example, suppose I created a cluster 1 which had a size of 100 observations. Then after creating the cluster 1, I will put these 100 observations back into the population, and from the entire population I will again create another cluster, and that cluster will have the same size, the size of 100 observations. So similarly, I create say 50 such clusters. I have 50 such clusters where each cluster is of the same size. In a one-stage cluster sampling, what happens is, out of the 50 clusters, we randomly select few clusters to form the entire sample size. So we require 2000 observations in our sample. So we will draw 20 random clusters. So suppose I selected cluster 3, I selected cluster 7, cluster 8, and so on. I selected 20 such clusters where each cluster have a size of 100 observations. So I will have my total sample with a size of 2000 observations. So this is the one-stage cluster sampling. So in a two-stage cluster sampling, what happens is, the process of dividing the population into clusters remain the same. Out of the clusters that we have generated, in this case we generated 50 clusters. we randomly select few clusters, and within each cluster, we randomly select few observations, and together we form a sample size of 2000 observations. So suppose in this case we select randomly 25 clusters. So I have cluster 1, cluster 7, cluster 9 and so on. I have 25 clusters with me, and within each cluster I will select 80 observations in a random fashion. Within cluster 1, suppose I randomly selected 80 observations. Within the cluster 7, I randomly selected 80 observations, and so on. So I will have 25 clusters, and within each cluster I have randomly selected 80 observations. So this will form my entire sample of 2000 observations. So again, within a two-stage cluster sampling, we divide the entire population into clusters. In this case, we divide into 50 clusters. Then within the clusters, we select few clusters in a random manner. In this case, out of 50 clusters, we randomly selected 25 clusters. And within each cluster, we randomly select few observations. So in our case, we randomly selected 80 observations from each cluster, and we had 25 such clusters, so which gave us in total 2000 observations. So this is the two-stage cluster sampling method. In stratified random sampling, all the stratas are included or represented in the final sample, and only specific elements within each strata are selected in the sampling unit. That is, suppose this is the entire population, and we divide the entire population into stratas. So within the final sample, that is, within the stratified random sample, we create few observations from strata 1 is included, few observations from strata 2 is included, and few observations from strata 3 is included. So within the stratified random sample, all the strata are represented in the final sample, but only few elements from each strata is represented in the final sample. But in case of clustered sampling, specifically the one-stage cluster sampling, only the sampled, that is, only selected clusters are included and not all the clusters, and all the elements within each selected cluster is selected in the final sample. So suppose this is the entire population, and we divide the entire population into say 50 clusters. So in the final sample that we have, it comprises of only few clusters. So say within 50 clusters, we randomly select 10 clusters. So in the final sample, we have only few clusters from the total clusters that we created, and all the members of each selected clusters form the part of the sample. Unlike stratified random sampling, where only few observation of the stratas form the part of final sample, here all the members of the selected cluster form the part of the final sample. So specifically speaking of the one-stage cluster sampling, only the selected clusters are included in the final sample and not all the clusters, and all the elements within each selected cluster is selected in the final clustered sample. Clustered sampling yields low accuracy because the cluster or the subsample created from the cluster might not be an accurate representation of the population, but still it is the most time and cost efficient probability sampling method. And clustered sampling method is commonly used for surveying the large markets or the broad markets. So the second kind of sampling methods, which are the non-probability sampling methods. In probability sampling methods, every member of the population had an equal chance of getting represented in the sample. But in a non-probability sampling methods, not every member have an equal chance of getting represented. The methods rely not on some fixed selection process like the probability sampling methods, but these methods rely on the researcher's capability of the sample selection. These methods rely on the researcher's judgment and researcher's skill in sample selection. So we have two non-probability sampling methods. First we will look at the convenience sampling method, and then we look at the judgmental sampling method. So starting with the convenience sampling. In convenience sampling, an element from the population is selected based on whether or not the element is accessible to the researcher, or how easy it is for the researcher to access the element. So if in a population there is a particular portion of the data which is not that easily accessible to the researcher, then those data have less chance of getting selected in the sample. So using convenience sampling method, samples can be collected quickly and at very low cost, but by sacrificing the accuracy of the sample, because the sample collected in such way might not be an accurate representation of the population. But still, the convenience sampling method is suitable in certain cases. When there are cost constraints, convenience sampling can be used. And also, convenience sampling can also be used when an analyst, before conducting a large scale and a more representative sample, wants to conduct a small scale study. Then convenience sampling methods can be very helpful. So using convenience sampling method, he can quickly collect the sample at a very low cost so that he can have a rough understanding of what the population looks like before conducting a large scale and before creating a more representative sample. So convenience sampling is very useful for small scale pilot studies. The second type of non-probability sampling method is the judgmental sampling method. Under judgmental sampling method, the researcher selectively handpicks the elements from the population based on his knowledge and his judgment. But the accuracy of the sample could be affected by the researcher's bias. The judgmental sampling methods are used when there are some time constraints, as well as when the speciality of the researcher is more important in selecting a sample, then judgmental sampling method is preferred over any other methods. So for example, an auditor who is auditing the financial statements and other documents of the company, the auditor does not go through all the transaction or the data. Rather, he picks certain data, he picks certain transaction which he thinks might provide sufficient coverage of the financial statements. So a seasoned auditor who is experienced and skillful, selects accounts or selects the transaction in such a way which accurately represents the financial statements condition. So when the specialty of researcher is more critical in selecting a sample, judgmental sampling method is more useful. So let us look at an example. I want you to solve this example and all the three questions. So if you have solved the questions, the correct answer to question 1 is option C. The correct answer to question 2 is option B, and for question 3 it is option B. Again, this question is also pretty straightforward. The correct answer to this question is option A, judgmental sampling. So if you guys have time, I would strongly recommend you to read through this demonstration. The main point that this demonstration is trying to prove is that as the size of the sample increases, the sample becomes a more accurate representation of the population. That is, the sample stat becomes a good estimator of the population parameters. This is represented by the mean absolute error. So you don't need to go into detail about the mean absolute error. Roughly speaking, you can consider it as the sampling error. So as the sample size increases, the error keeps on decreasing. That is, the sample stat now becomes more closer to the population mean. It becomes a better estimator of the population mean. Similarly, in case of stratified random sampling, as the sample size increases, the error keeps on decreasing. But there comes a certain point where the analyst needs to decide between the increased accuracy by increasing the sample size versus the increased effort and cost by increasing the sample size. So by increasing the sample size from say 200 to 500 definitely increases the accuracy. But the analysts need to decide whether the incremental accuracy is justified given the cost and the effort required to collect a huge sample. So there is a trade-off between the cost and the time involved versus the accuracy. So as the sample size increases, the accuracy of the sample statistic to predict the population parameter also increases. Now, having said that, it is not always the case that a larger sample size does a good job of predicting the population parameters. For example, an analyst must be careful while sampling from a population data which follows more than one distribution, or when the population data is not consistent over time. So suppose we are evaluating a portfolio manager's performance. We are evaluating the daily returns of the portfolio manager for the past 50 years. So the population data consists of 12,500 observation. Now suppose during the first 30 years, the portfolio manager followed a low risk strategy, and during the next 20 years, the portfolio manager followed a high risk strategy. So the population data in the first 30 years might not have the same characteristic as the population data of the next 20 years. Say the population data in the first 30 years might follow a particular distribution, whereas the data in the next 20 years might follow a different distribution. So creating a larger sample size to represent the entire 50-year population data might not be accurate. So instead, even selecting a smaller sample size, but ensuring that the smaller sample size represents only a particular population data which is homogeneous over time, which is consistent over time. So similarly, for the next 20 years, we can even draw a smaller sample size, but ensuring that the population data is consistent over time. So it is not always necessary that a larger sample size is always better. If we draw a larger sample size from a population which is not consistent, then even the larger sample size might not be an accurate representation. So the analysts need to be careful when a population data follows more than one distribution, or when the population data is not consistent over time. Third section, which is the central limit theorem and the inference about population. This is one of the most important section of this chapter. So suppose we have a population data, and from this population we draw a random sample. This population has a mean of mu, and this sample has a mean represented by x bar. Ideally, we want the sample mean to be as close as the population mean, but still no sample is 100% accurate. There will be some difference between the population mean and the sample mean, and this difference is referred to as the sampling error, which is the difference between the sample mean and the population mean. But practically speaking, we will never be able to know what a population is. Therefore, we will never be able to understand the sampling error or how closely is the sample mean representing the population mean. Then here sampling distribution and the central limit theorem helps us in understanding how close is the sample mean to the population, what is the difference between them, or what is the error between the sample mean and the population mean. So let us first understand the sampling distribution. Then on the next slide, we move on to understand what the central limit theorem is. Suppose we have a population, and from this population we randomly draw a sample. This sample has a sample mean. Let me write this sample as sample 1 and this sample mean as sample mean 1. So I put this sample back into the population, and from the entire population, I draw another sample. Say this is sample 2. So this will have sample mean 2. Similarly, I draw 100 such samples and I will have 100 samples and 100 sample means. When we plot all these sample means on a graph, this is referred to as the sampling distribution. So suppose we plot all these data, all these sample means on a graph, and we get a distribution something like this. This is referred to as the sampling distribution of the sample means. So a sampling distribution of a sample mean refers to the distribution of sample means computed from the samples of the same size, and these samples are randomly drawn from the population. So let us look at the following exhibit. In this exhibit, we collected 100 samples. So in the first table that we are seeing, in the first graph that we are seeing, we have 100 samples where each sample has a size of 10. And in the second graph, we still have 100 samples and each sample has a size of 50. We have two more graphs where we have 100 samples and the sample size in the third graph is 100 and the sample size in the fourth graph is 300. So as the size of the sample increases, the sampling distribution of the sample mean closely represents the normal distribution. So comparing this graph which has a sample size of 10 with the last graph which has a sample size of 300, we will find that this graph over here is more closely representing a normal distribution. It is more closely like a normal distribution compared to this graph which has a smaller sample size of 10. So on the next slide, we will understand how sampling distribution and the central limit theorem helps us find out the error or the difference between the sample mean and the population mean. Now we will look what central limit theorem is. Suppose I have a population and this population has a mean of mu, and I randomly draw a sample from this population and this sample has a sample mean of x bar. We want to know how much does this sample mean deviates from the population mean. How much does it vary from the population mean? Because we don't actually know the population mean, so we won't be able to find this directly. So we use the central limit theorem, which helps us in finding out how much does the sample mean deviates from the population mean. Now listen to this carefully. Assuming that if we withdraw hundreds of sample from the population, where each sample has the same size, and the size should be equal to the sample that we have actually drawn. So suppose the size is 50 observation. So the hundreds of sample that we draw, each sample should have a sample size of 50 observation. So the central limit theorem states that if we plot all the sample means, the hundreds of sample means, the sampling distribution of the sample mean will follow a normal distribution, given that the sample size is large enough. So the sampling distribution of the sample mean will be normally distributed, and average of all the sample means will be approximately equal to the population mean, and variance or the standard deviation of this distribution will be root of the population variance divided by the sample size. And this is what we are concerned in the central limit theorem. Suppose the standard deviation comes out to be 1.8%. Now what does the standard deviation of 1.8% means? It means on an average each variable, in this case the variable is sample mean, on an average each sample mean deviates 1.8% from average of all the samples. In this case, average of all the observation is the population mean. So we can say that on an average, the sample mean deviates 1.8% from the population mean. So similarly, the sample that we have drawn, the sample mean deviates 1.8% from the population mean. Now you should have one question, that if we have the population mean with us, then why do we even need to draw a sample and to find out how much does this deviate from the population mean? We directly have what we require, but we don't actually withdraw hundreds of samples from the population, because it becomes very difficult to draw hundreds of samples from the population. It will be as good as studying the entire population. So because we don't actually withdraw hundreds of samples, we actually won't have the population mean with us. Therefore, we need to use the variance to estimate how much does this sample mean varies from the population mean. Now even this formula, that the variance formula, is an approximation. The actual formula of a standard deviation is, we take each variable, which is sample mean, subtract average of all the observation, which is the population mean, we square it, we add all the deviation squared, divide it by number of observations minus 1. We take the square root of this. Suppose the answer to this standard deviation is 2%. We can say that the sample mean deviates 2% from the population mean. But it is not possible to use this formula because we don't have the data of hundreds of sample mean, nor do we have average of all the sample means. So the people who developed central limit theorem came up with this approximation of the standard deviation, which is the square root of the population variance divided by the sample size. And if the population variance is not available, then we can use variance of the sample we have withdrawn. So variance of the sample we have withdrawn divided by the sample size, and we take square root of this and we get variance or the standard deviation of the distribution. And the standard deviation of this distribution will help us in finding out how much does the sample mean deviates from the population mean. So this is the formula we are interested in. And this is the official definition of the central limit theorem, which says that given a population data described by any probability distribution which have a finite mean mu and a finite variance sigma square, then the sampling distribution of the sample mean x bar computed from random samples of size n from this population will be approximately normally distributed, with average of all the samples being the same as the population mean mu and the variance being the population variance divided by the sample size, given that the sample size should be large enough to satisfy all these things. Now generally speaking, when the sample size is 30 or greater, it is sufficient enough to satisfy the central limit theorem. So central limit theorem therefore allows us to make some quite precise probability statements about the population mean by using the sample mean, regardless of what the distribution of population data is. Even if the population is positively skewed, or if it is negatively skewed, or if it is platykurtic, leptokurtic, it doesn't matter. No matter what is the distribution of the population, the sampling distribution of the sample mean will always be normally distributed, given that the sample size is large enough. So the central limit theorem stated that the variance of the sample means distribution is the population variance divided by the sample size. The standard deviation of the sample means distribution is known as the standard error of sample mean. So if we take root of this, we get the standard deviation of the sample means distribution, and this standard deviation is referred to as the standard error of sample mean. So when the population standard deviation is known, then the standard error of sample mean is population variance, population standard deviation divided by root of the sample size. And when the population standard deviation is not known, we use the standard deviation of the sample we have drawn. So the standard error of the sample mean equals to the standard deviation of the sample divided by the sample size root. And how do we calculate the standard deviation of a sample? We take summation of the squared deviation. That is, if in a sample we have 50 observation, then we take deviation of each observation from the mean of the sample squared. So we add all the 50 deviation squared divided by number of observation minus 1. So this is the formula. So the variance of the sample equals to summation of all the deviation squared divided by n minus 1. And taking root of this, we will get the standard deviation of the sample, which is this. So standard error of the sample mean helps us in understanding how precise is the estimate from its true value. That is, how much does the sample mean that we have calculated from the sample drawn, how much does this sample mean vary from the population mean. So the main point of central limit theorem was to help us find out the standard error of the sample mean. So we can understand how much does the sample mean deviates from the population mean. Let us solve the following example. A research analyst make two statements about the repeated random sampling. Statement 1 is, when repeatedly drawing large samples from the dataset, the sample means are approximately normally distributed. Yes, this seems to be accurate. The statement 2, the underlying population from which the samples are drawn. The underlying population must be normally distributed in order for the sample means to be normally distributed, regardless of what the population distributions are. The sample means distribution will always be normally distributed, given that the sample has a large enough size. So which of the following best describes the validity of analyst's statement? So the correct option is option C, where statement 1 is true and statement 2 is false. Peter Biggs wants to know how growth managers performed over the last year. So Biggs assumes that the population's standard deviation is 6%. Then how large a random sample does Biggs need if he wants the standard deviation or the standard error of the sample mean to be 1%? Here we know the population standard deviation. So the standard error of the sample mean equals to the population standard deviation divided by root of the sample size. We are given the standard error, which is 1%, and we also have the population standard deviation, which is 6%. We are required to find out the sample size. Rearranging the equation, we get n as 36. So the sample size should be 36 in order for the standard error to be 1%. How large a random sample does Biggs need if he wants the standard deviation or the standard error of the sample mean to be 0.25%? So again, using the same formula, we get the sample size required to be 576. We are done with the most important section of this chapter, which was the central limit theorem. Now we look at bootstrapping and the empirical sampling distributions. Suppose this is the population data. So the central limit theorem that we have studied stated that if we draw hundreds of samples from the population data where the sample size is large enough, then we will have the sampling distribution of the sample mean, which is approximately normally distributed. So based on this sampling distribution, which arrived from hundreds of sample, based on this sampling distribution, we can make some inferences about the population parameters. we can estimate how far away is the sample mean from the population mean. So this was the central limit theorem. The second approach could be the resampling method, where from the population data, we draw a sample, and from this sample itself, we draw hundreds of different possible samples. This method is referred to as resampling and is a great alternative to what the central limit theorem has to say. So resampling refers to repeatedly drawing samples from the original sample for making inferences about the population parameters. Two of the most important resampling methods are the bootstrapping resampling method and the jackknife resampling method. We will be looking at the bootstrapping method in detail, and the curriculum does not go into detail about the jackknife resampling method. So we will have a broad overview of what the jackknife method is. Over the next few slides, we will be understanding what bootstrapping method is. Now let us understand what is the bootstrap resampling method. So suppose this is the population data that we have, and from this population we randomly take out a sample, and from this sample we take out various samples, and these are referred to as resamples. So we have resample 1, we have resample 2, and suppose we take 100 resamples from the original sample, and the size of each resample will be the same as the original sample. Suppose the original sample had a size of 500, so each resample will also have a size of 500 observations. So let us see in detail how is a resample created from the original sample. Suppose this is the original sample that we have, and we have 500 observations in the original sample. We have 500 observations. From this original sample, we create a resample, say resample 1. So even resample 1 will have 500 observations. So what we do is, from the original sample, we randomly pick one observation. Suppose that observation was the third observation. Then we put this third observation back into the original sample. Then again, from the 500 observations, we randomly pick an observation. Suppose that observation comes out to be the 79th observation. We again put this back into the original sample. So again, from the 500 observations, we randomly pick an observation. So it is possible that we could have the third observation repeated twice. So it is possible that some of the elements from the original sample might be repeated 2 times or more, and it is also possible that some of the element from the original sample might not at all be included in the resamples. So in this way, we have resample with 500 observations. Similarly, we create multiple such resamples where each resample have a size of 500. So this is the bootstrapping process. In a bootstrap, we repeatedly draw samples from the original sample, and each resample is of the same size of the original sample, and each element that has been drawn from the original sample is replaced for the next draw. That is, each element that has been drawn is put back again into the original sample so that it can be drawn for the next time. So some elements from the original sample may appear several times in a resample, while other elements may not appear at all. Now the question arises, why do we even need to bootstrap? Why do we need to create so many resamples from the sample? What is the objective? So if you remember the central limit theorem, according to central limit theorem, from the entire population, if we draw multiple samples, suppose we have n samples, then we have n sample means. And if we plot all the sample means on a graph, this is referred to as the true sampling distribution. And this will approximately follow a normal distribution, where average of the distribution will be the population mean, and the standard deviation or the standard error of this distribution. The standard error of the sample mean will be population standard deviation divided by root of the sample size. And if you remember, I told you that this was an estimate of the original standard deviation of this sampling distribution. The original standard deviation uses the same formula as the other standard deviation. That is, the original standard deviation's formula is summation of the deviation of each sample mean from the population mean squared divided by the number of sample means that we have minus 1. So this is the actual standard deviation of the sampling distribution. But because we don't have the data of all the samples, we took an approximate of the standard deviation, which is represented by this formula. So Bootstrap helps us in finding out the original standard deviation of this sampling distribution. That is, the Bootstrap helps us in finding out the actual standard error of the sample mean rather than using this estimate of the standard error of sample mean. So this is the Bootstrap process, where from the total population we draw a sample and we treat this sample as our population. So this is the original sample. From this original sample, we take out multiple samples. These are either called as resamples or bootstrap samples. So in total we have B bootstrap samples and we will have B sample means. So if we put all these estimates on a graph, we will get a bootstrap sampling distribution. And this bootstrap sampling distribution exactly mirrors the true sampling distribution. That is, the standard deviation of the bootstrap sampling distribution will be almost equal to the standard deviation of the sampling distribution, the true sampling distribution. So because we have the data of all the estimates of all the bootstrap sample means, we can find out the standard deviation of the bootstrap sampling distribution. Then this standard deviation will be almost close to the standard deviation of the true sampling distribution. So I can say this standard deviation is almost close to the standard error of the sample mean. Now the question might arise, as the bootstrap sampling distribution exactly mirrors the true sampling distribution, then whether the average of all the estimate is the population mean, just like the average of all the sample means here was the population mean. The answer is no. Only the standard deviations of the two sampling distributions are the same and not the average value. The average value in a true sampling distribution is represented by mu, which is as good as the population mean, and the average value in a bootstrap sampling distribution is represented by this symbol. Now let me illustrate how is it possible that we can have two distributions which have the same standard deviation but different averages. So suppose we have two distributions, the first distribution and the second distribution. Suppose the first distribution has a mean of 7% and the second distribution has a mean of 2%. So we will have 10% over here, we will have 13%, we will have 16%. On the left side we have 4%, we have 1%, negative 2%. Similarly, for the second distribution, we have 5%, 8% and 11%. And on the left side, we have negative 1%, negative 4% and negative 7%. So, the 10% is one standard deviation away from the mean of 7%. Similarly, 13% is two standard deviations away from the mean of 7%. Similarly, in the second distribution, 5% is said to be one standard deviation away from the mean. Similarly, negative 1% is one standard deviation away from the mean. So, standard deviation in the first distribution is 3%. Standard deviation in the second distribution is 3%. So, even though both the distribution have the same standard deviation, but their means are different. So it is possible that we can have two different distributions which have the same standard deviations but they have different means. So similarly, true sampling distribution and the bootstrap sampling distribution have the same standard deviation but they have different means. So we use the bootstrapping method to estimate the standard error of the sample mean, or we can say the standard deviation of the true sampling distribution. So what is the formula of the standard deviation of the bootstrap sampling distribution? The formula equals to summation of the deviation squared divided by the number of observations minus 1. Here number of observations are represented by capital B. So we have B minus 1 and each sample mean is represented by this symbol over here. So this is the observations, these are the random variables, and we subtract the average. The average is represented by this symbol. So we subtract the average from it. So the deviation of each observations from the sample squared, we take summation of all these deviations squared divided by number of observations minus 1. So this standard deviation of the bootstrap sampling distribution is same as the standard deviation of the true sampling distribution. So this is the formula of the standard deviation of the bootstrap sampling distribution. So in the formula we have summation of the deviation squared divided by number of observations minus 1. Now let us look at an example and things will be much clear. Now let us look at an example of bootstrapping. So we have a rarely traded stock. Suppose that stock is XYZ and the population consists of 1000 monthly returns. So we have 1000 monthly returns of this rarely traded stock. So out of the 1000 monthly returns, we randomly pick a sample. Our sample consists of 12 monthly returns. The sample mean comes out to be negative 1.40%. We are required to find out how much does the sample mean deviates from the population mean. That is, we are required to find out the standard error of the mean, and we will be using the bootstrap resampling method to find out the standard error of the mean. So let us read the example. Exhibit 6 displays set of 12 monthly returns of a rarely traded stock, which is shown in column A. So these are the 12 monthly returns. This is our original sample and the sample mean is negative 1.40%. Our aim is to calculate the standard error of the sample mean. So we will be using the bootstrap resampling method. A series of bootstrap samples labeled as resamples are drawn from a sample of 12 returns. That is, the resamples are drawn from the original sample. Now notice how some of the returns from the original sample feature more than once in some of the resamples. So in resample 1, as we can see that we have 0.055 repeating 2 times. So this is the first time and this is the second time. And some of the observations from the original sample are not there in resample 1. So this is called as the replacement method. So from the original sample, we have 1000 resamples and we have 1000 sample means. We have 1000 sample means. So the standard deviation of these sample means, that is standard deviation of the bootstrap sampling distribution, will be equals to the standard error of the sample mean. So now let us find out the standard deviation of these bootstrap sample means. Drawing 1000 such resamples from the original sample, we obtain 1000 bootstrap sample means, and we have the standard deviation of the bootstrap sample means. That is, we have the standard deviation of the bootstrap sampling distribution, which is 4.408%. This standard deviation of bootstrap sampling distribution is almost equal to the standard deviation of the true sampling distribution or the standard error of the sampling mean. So we can say that the standard error of sampling mean comes out to be 4.408%. So if you remember, the sample mean was negative 1.40%. Now how do we use the standard error of the sample mean to make some inference about the population mean? So we can say the sample mean deviates about 4.408% from the population mean. So our population mean could be negative 1.40% plus 4.40%, or the population mean could be negative 1.40% minus 4.408%. So our population mean could either be 3.008% or our population mean could be negative 5.80%. So this is how we use the standard error of sample mean to make some inferences about the population mean. And this is how we use the bootstrap sampling distribution to find out the standard error of sample mean. Bootstrapping is also referred to as model-free sampling or non-parametric sampling, unlike the central limit theorem. If you remember that for central limit theorem to satisfy, for central limit theorem to work, the population should have a finite mean and the population should have a finite variance. That is, the central limit theorem will work only if certain parameters are satisfied. But this is not the case with bootstrapping. Irrespective of what the population parameters are, bootstrapping will still work. That's why it is called as model-free sampling or non-parametric sampling. Bootstrapping does not depend on the parameters of the population. But one similarity between bootstrapping and the central limit theorem is that in central limit theorem, irrespective of what the population distribution is, the true sampling distribution will always follow a normal distribution, given that the sample size is large enough. Similarly, in bootstrapping, irrespective of what the original sample's distribution is, the bootstrap sampling distribution will always follow a normal distribution. That is, the bootstrap sampling distribution will always be similar to the true sampling distribution. And unlike central limit theorem, bootstrap does not rely on any analytical formulas. So for finding out the standard deviation of the true sampling distribution, we did not use the actual standard deviation formula. Rather, we used an approximation. We used this formula to find out the standard deviation. Whereas in bootstrap, we use the actual standard deviations formula to find out the standard deviation of the bootstrap sampling distribution, and we don't use any approximation. And bootstrapping can also be used to estimate the standard error of statistic of other population parameters like median, which do not apply to previously discussed method. So the central limit theorem can be used to find out only the standard error of sample means. It cannot be used to find out standard error of the sample medians, whereas bootstrap can be used to find out the standard error of sample mean as well as sample median and other population parameters too. So bootstrapping has many advantages over the central limit theorem. Now let us look at the second type of resampling method, which is the jackknife resampling method. You won't be tested much on the jackknife resampling method, as in the curriculum you are only given a broad overview of what this resampling method looks like. So let us look at a broad overview of what this method is. In jackknife resampling method, we repeatedly draw the resamples from the original sample without any replacement. So suppose this is the population, and from this population we draw a sample. This is the original sample, and suppose the sample has a size of 5 observation. So we will create resamples from this original sample. So the number of resamples will depend on how many observations we have in the original sample. So in this original sample we have 5 observations. So we will have 5 resamples. We have resample 1, resample 2, 3, 4 and 5. Now let us see how do we create each resample. Suppose this is the original sample that we have and we have the following observations. We have 5 observations. So from this original sample, we create a resample 1. We create this resample by leaving out one observation. So suppose we leave out the first observation this time. So from the remaining 4 observations, we will create our resample. So suppose from the remaining 4 observations, I randomly pick up an observation and that observation comes out to be the 4th observation. And without replacement, that is, without putting this observation back into the original sample, I will now pick up an observation only from the remaining 3 observations. I am not allowed to repick this observation that I have already drawn. So from the remaining 3 observations, suppose the observation I picked was the 3rd observation. Now I am only allowed to pick up from these 2 observations. Suppose I have the 5th observation. Now I am left with only the 2nd observation. So this is the resample 1. In resample 2, suppose we now leave out the 2nd observation. So the resample 2 will have the 1st observation, the 3rd observation, the 4th and the 5th observation. Similarly, in the resample 3, we leave out say the 3rd observation. So we can say if the original sample has a size of n, then the resamples will have a size of n minus 1. So the original sample had a size of 5 observation and each resample had a size of 4 observation. And for original sample of a size 5, we will have 5 resamples. So resamples are selected by taking the original sample and leaving out one observations at a time. So for original sample size n, each resample will have n minus 1 observations and we will have a total of n resamples. So this is how resamples are generated in jackknife method. Jackknife resampling method is often used to reduce the bias of the estimator. Now let us look at the following example. I hope you can solve this example, and if you have solved the example, the correct answer is option B. We cannot use the central limit theorem to find out the standard error of sample median, whereas we can use the bootstrap method to compute the standard error of sample median. The second question, Otemachi has a spreadsheet with 108 monthly returns for the shares in Murnau Corporation. So the original sample has a size of 108 observation. And he writes a software program that uses the bootstrap resampling to create 200 resamples of Murnau data, that is our original sample, by sampling with the replacement. Each resample has the same size of the original sample, which is 108 data points. Chi's program calculates the mean of each of the 200 resamples, and then it calculates that the mean of this 200 resample mean is 2.61%. That is, the average of all the resample mean comes out to be 2.61%. The program then subtracts the average, which is the 2.61%, from each of the 200 resample means. Then square each of these 200 differences, that is, squares the 200 deviations and adds all the squared deviations together. So the sum of all the squared deviation comes out to be 0.835. The program then calculates an estimate of the standard error of sample mean. So what is the estimated standard error of the sample mean? So the formula of the standard error of sample mean, or the standard deviation of the bootstrap sampling distribution, equals to the root of summation of the squared deviation of all the observations from the average divided by total number of free samples, or total number of free sample means minus 1. So in this example, summation of all the squared deviation is 0.835 and total number of free sample means are 200, and we subtract 1 from it. So the standard deviation that we get is 0.0648, that is 6.48% is the correct answer.